Hello, my name is Amy Kessel, and I am a graduate student with Dr. Yoon Sub Song with the University of Nebraska-Lincoln. And I'm here to discuss this idea of integration of metabolic network and data-driven modeling with its use in predicting microbial interactions. To start, we're going to talk about context dependency and how microbial interactions are context dependent. That is, we can see shifts in either the strength or the sign of the interaction as biotic or abiotic context change. Now, these biotic or abiotic context changes can be anything from historical, it can be membership, such as the addition of a new species, it can deal with changes within a host itself, or it can be changes within an environment. And these environmental changes can vary quite a lot. And we can take a look at stuff such as the increase in toxicity of an environment, or looking at the increase of resources available within an environment. And we can then look at microbial interactions and how they change with either increasing toxicity or increasing resources. Using this idea, we're going to look at shifts in interactions between competition and cooperation and look more specifically at nutrient availability. To do this, we're using a binary model of oxytrophic tryptophan and oxytrophic tyrosine. Now, these mutant E. coli simply are lacking the ability of producing a specific amino acid. In this case, delta tryptophan cannot produce tryptophan, and delta tyrosine cannot produce tyrosine. Thus, in a two-model system of the two, they have to depend on each other to get the amino acid that they cannot produce. That's where the cooperation comes in. However, they're both mutant E. coli. They both grow on glucose, thus they both need glucose available. That's where the competition comes in. So we can actually take a look at how these microbial interactions change with changes of these nutrient availabilities. As an example, with excess glucose, they're not going to be competing for glucose since there's enough around. Instead, they're simply going to have a mutualistic relationship where they're going to constantly share tryptophan and tyrosine with each other. When we're looking at excess of amino acids, then they don't need to get it from their partner, so there's no longer that mutualistic interaction between the two. Instead, we're simply going to see competition where they are fighting for glucose. We can instead look at what's happening when we have one or the other amino acid excess and what happens then. So using this idea of interaction shifts for nutrient conditions, we can take a look at these interaction shifts and how these cultures grow in these different nutrient conditions. And we do this by doing this binary growth of the oxytrophic tryptophan and oxytrophic tyrosine under two different scenarios, either batch or fed batch. The two of them are the same, that is, they're both grown together. The only difference is in the fed batch, we simply add these feed beads, glucose feed beads, at time 7.5 hours. And we see how the two of them grow. Now, keep in mind, we're not growing them separately because they are oxytrophic. They cannot grow by themselves separately, so we will grow them in a binary culture. Now, with this idea in mind, taking a look at this first graph, we see that as glucose decreases, seen in black, then we have our oxytrophic tryptophan in blue and our oxytrophic tyrosine in orange, both increasing until glucose hits zero, and at that point they stop growing. This can be seen as well on the bottom. The bottom is the same concept of binary growth. The only idea is now the two of them are shown as one biomass together. The fed batch data shows something very similar. The only difference is at time 7.5, we have this glucose being added, and so we see a bump in our black line to show glucose concentration. So glucose concentration jumps up for just a very quick time. But what this means is we can use this data and we can try and model it. Well, how can we model this? How can you model context-dependent interactions? There's a couple different methods. One of them is generalized Lotka-Volterra models. These are great. They strictly show the rate of change of a species growth in terms of both itself as well as any of the species within the community. And we have three different things that we have to keep in mind. First of all, we have basal growth rate, that is the growth of the organism by itself. Interspecies interaction coefficient, that is the growth of the species itself and how it affects future growth. And then finally, interspecies interaction coefficient. That's going to be how its partner in the culture will affect itself. Problem with GLV models is they assume all of these coefficients are constant. And as such, they're not effective in modeling a dynamical interactive change. Kinetic models are. We can use kinetic models to capture these dynamic context-dependent interactions. And that's because if you take a look at these models, we have these substrate, glucose, tryptophan, or tyrosine, and they themselves can be written as a function themselves. So we can show change in concentration of glucose or either of the amino acids over time. And since these values will constantly change, then this becomes dynamical. Problem with the kinetic model for the Monod-Michaelis-Menten model is it has a lot of parameters, and finding these kinetic parameters can be very challenging. Secondly, we can't actually quantify interactions with this. So we need something that's going to be dynamical, but not as challenging as kinetic modeling. Well, we've decided to go back to the generalized Lotka-Volterra model and determine a few things. First of all, this basal growth rate is actually 0. They're auxotrophs, so it doesn't exist. Secondly, interspecies interaction coefficient can be considered constant, and that has to deal with the fact that this idea of its growth by itself is actually more density dependent than it is related to environmental variables. So that environmental variables are actually pretty weak. So we can look at these as just being constant values. Lastly, this A12, A21, our interspecies, we can now look at that more specifically. And we can look at it as a relationship of environmental variables. We can make it a function of their variables. To do this, we can model them as polynomial functions. So notice for A12 and A21, they're the same sort of polynomial functions where it's a constant plus glucose plus tryptophan plus tyrosine and so forth to the nth degree using Taylor expansion. And we can then determine what these values are by using SINDI. That is determining the coefficients using SINDI. SINDI is our data-driven modeling approach, known as sparse identification of nonlinear dynamics. And the idea behind this is we're able to look at a nonlinear dynamical model, input its data, and knowing its derivative, we can actually write it out as a function of all possible terms that we can think of, and then figure out their coefficients. And when we multiply this all together, we get an output model. And this identified system, the closer it is to the data input, the better the model. We can actually then make this a sparse model by limiting the number of coefficients that we have available to us using a sparsity knob by the user. What's even better is because of mechanistic insight, we can actually modify this library of possible interactive terms and only include those that fit our dynamical term of interest. So using SINDI, we get some great data with this. SINDI predicts the decrease in interspecies interaction in time among individual data sets. When we build our model using a batch data set, we see these decreasing interaction coefficients for both A12 and A21, that is for both species. And this does make sense because interspecies interaction should be large to begin with. They're auxotrophic species, meaning that they're very dependent on their partner to begin growth and thus should have high interaction. But as time goes on, glucose becomes more limited. As glucose becomes more limited, we have more competition. With more competition, lower interaction coefficient. This is seen again in the fed batch data. When we build our model on fed batch data only, we see again this decrease. And not just that, we actually see this little bump. And this little bump, while it just looks very, very small, it's at time 7.5 hours. And that is when we add our glucose feed beads. So we're seeing that the model does indeed show some of the stuff that we expected from the actual data. But this little bump is really small, and it could be that we are overfitting our data. Thus, to correct this, we decided to instead build a model by data fitting over all our data sets. And when we fit over all data sets, we see that we actually have better results. We see more improved and more minute changes in these interaction coefficients with more data sets used. And even better yet, if you take a look at this fed batch data at time 7.5, we do see a much better scenario for what's happening with this jump in glucose. And we can conclude that interspecies interactions are positively correlated to glucose availability. This itself is just part of the story. The problem is knowing this doesn't actually tell us what's happening with the metabolic pathways themselves, but we can use this and integrate it with metabolic network modeling to look at these metabolic pathways. We can use metabolic network modeling such as flux balance analysis, that is a mathematical approach that determines metabolic fluxes within genome scale metabolic models. So we have genome metabolic models such as IEF 1260 E. coli, which is a E. coli model built over a number of years by very well-established scientists, and we can update it to a mutant E. coli by simply removing reactions that will help produce tyrosine or tryptophan, thus making it impossible to grow without the available amino acid. And that's strictly done by just removing whatever reactions we need and seeing if they grow without tryptophan or tyrosine. Then we can run FBA, run flux balance analysis, and see what kind of biomass we have and look at these metabolic fluxes to determine the pathways at different states. We see first that biomass yield is positively correlated to this glucose and amino acid uptake rates, which does make sense. Our organisms do require both to grow, so if we have more available, we should have larger biomass yield. Secondly, biomass yield is more finely tuned to amino acid uptake rate. So the smaller the amino acid uptake rate values here, even though this change between the values are very small, we actually do have a larger change in biomass than with glucose itself. And secondly, we see that the oxytrophic tryptophan E. coli has a higher biomass rate than the tyrosine E. coli at similar amino acid uptake rates. And this does confirm with our data. We knew that we should have larger amounts of tryptophan available than tyrosine available over time, and that tryptophan will grow quicker than tyrosine. So all this does add up. And then we can take a look at what's happening with biomass yield at specific time points. So looking at time point 1, we can then see what happens with time. As time goes on, we see that biomass yield actually decreases. So by the time of time point 24, biomass yield for the delta tryptophan, oxytrophic tryptophan that is almost 0. So biomass yield is decreasing with time. For the tyrosine oxytroph, it is still decreasing, not as much. However, keep in mind, because it's partnered with tryptophan, when tryptophan oxytroph can no longer produce, it will no longer be able to produce tyrosine either, and thus our tyrosine oxytroph won't have any tyrosine to work with. It too will eventually drop to 0 very quickly. So with this in mind, we can now look at metabolic pathways and see that we do see some very interesting changes in metabolic pathways. First of all, with this delta tryptophan E. coli, metabolic pathways do shift from glycolysis to gluconeogenesis with decreasing nutrient availability. We see with high glucose, we have glycolysis, which makes sense. We have a lot of glucose available. The model will want to try and break it down. I should say the organism will want to break it down. However, when we run out of glucose, when we're very limited in glucose, we're no longer going through glycolysis. Instead, we're going to try and build any bit of glucose we can using gluconeogenesis. Secondly, because of this gluconeogenesis at time point 24, we see that at time point 24, we also have increased enzymatic activity of the pentose phosphate pathway with this limited glucose available. So there are very dynamic changes within the metabolic pathway themselves, which leads us to conclude the fact that, first of all, microbial interactions are context dependent. And since we need a generalizable model available, we suggest our data-driven modeling approach that will enable predicting dynamical variations of interactions as a function of these environmental variables, and then integrating them with metabolic networks to show how interaction shifts across contexts at reaction pathway levels. Now, keeping this in mind, our approach is extendable to multiple species, which does make it generalizable and useful in very many scenarios and many microbial communities. With this, I would like to acknowledge and thank first Dr. Song for all of the help that he's provided for me on this research project. I'd like to thank as well the DOE of Biological Environmental Research through a subcontractor with PNNL, for their continued support. I'd also like to thank all of you for taking the time and listening to me go through this. And if you have any questions, please feel free to come to my live Q&A on November 19th